process. Without process, there is no need of doing a process control. So this can be process or process model, whatever. If it is a hard, sometimes it is also called as hardware in loop simulation. So it would be just using a model. Then you have your measurement sensor. Okay. Okay, so then you have a something known as comparator. So comparator job is okay. Compare set point. So you need to have a set point that is fed into the comparator and actual measurement. So comparator would compare the what you call the actual measurement and the set point. Okay, then this information is going to the controller. Okay, so this is basically your error. So you need to nullify this error. There is something that is desired, and error is the undesirable component of the all. Okay, this error is so let me just draw an aroma. So this is the way that flow of things work. This comparator would feed in error to the controller. Okay, controller would of course give a controller output, and this would most likely go to an I2P converter, because you need to send into control valve. Before going to the control valve, you need to have a mechanism that converts this. So see, you have to check this is a physical variable. It could be temperature, pressure is a physical variable. From here onwards, these are all electrical signals. Because the sensor is going to convert your physical variable into an electrical signal, and it's all going inside electrical signal. And controller is also technically give you an electrical signal output, because we have seen the parallel architecture and series architecture wherein you have circuits used to implement the controller strategy, or you need to have a soft, or you need to have an DCS induced control system wherein the control algorithm is soft coded. Okay, so I2P converter onwards, I2P converter provides signals. From here onwards, things become pneumatic, because you need to operate a control valve which is most likely operated by pneumatic thing. And here you have your control valve. Okay, control valve or actuator, and this control valve is eventually connected to your process, because this is what it control. This is what controls your flow of, or maybe pressure or some certain variables, so that the changes to the process can be effected. So then this is the overall loop. So what I wanted to say is, this is eventually, if you look at this is actually forming a loop. If there is a change, and see, the process is also affected by disturbances which are known or unknown. So due to some disturbances in the process, your set point might not be matching with your actual measurement, and you do this exercise until your error value goes to 0. This is what the overall control system. So it looks simple, but let's say if you are looking for a large process having enormous number of variables, this exercise is going to be like really challenging to implement. So now coming to the system. So we were trying to see the individual components. So simplest component is of course the process, and the process would have two components. As I told you, would have a disturbance term and a what you call manipulated thing that you can manipulate by means of control. For instance, so look at this particular case. Okay, here you have kept control valve on this line. Here there is no control valve, this line. So even we assume that, okay, the flow rate is constant. I think that is assumption here. Okay, considering no variability is W1, is essentially means that this W1 is constant, but your X1 can vary. So flow rate constant doesn't mean that your composition is going to be the same. So this happens to be your disturbance into the system. So you have learned this, how to isolate the disturbance variable, because something that you don't have any control can be the disturbance system. For instance, if you are a let's say if you are doing a very high temperature controlled experiment, the room temperature changes the disturbance because you don't have any control on that. So this would change. So your overall transfer function should contain two components technically, a disturbance component and a relationship with respect to the manipulated variable, and its total summation is your output, because your overall output here contains this is the control or manipulated line. I'm sorry about that. So this is the manipulated line and this is the disturbance line. So you mix them up, okay, and finally get your output. So this is X which is measured, or which this is the final mixed up X. So you would have, so this is, let's say, so that's why the overall transfer function of X would contain contributions from the disturbance side and the manipulated side. Here there is no control, here there is no control, while here there is control. Okay, so now the next component is your transmitter. So transmitter, so this we have discussed, just started discussing it. So transmitter or even your sensor. So consider you are going to measure a temperature. Okay, so how do you do this? You have this maybe your water bath, and which may be getting heated, and this is water is getting boiled, and you need to measure the temperature inside this water bath. So what will you do? You would generally dip a thermometer, or simplest way, you could do various ways of measuring temperature. For instance, thermometer is the simplest. Okay, if you are doing it manually, and there are automated methods like RTD, resistor temperature detectors or devices, of course thermocouples, so on and so forth. So these would directly give you electrical signals corresponding to the temperature, while in thermometer you will have to go and measure the temperature. And you might have seen, like in various instances, when you dip the thermometer into the where you want to measure your temperature. For instance, even if you are trying to measure temperature of your body, so you may use the thermometer to keep either in your armpit or even inside the mouth. You would really see that it would take some time for it. So eventually it would show your temperature, but it would take some time to show the temperature. So if this is time and this is your steady state temperature finally, so I'll put, let's say, TF whatever, and this is T naught. So this is not immediate, so you would say that it would take some time. Initial responses would be fast. Okay, when you can look at when you look at your body temperature measurement. So suddenly, let's say if you start, so if it's a digital temperature, it will show yellow low. So then it would, let's say it would quickly go to maybe 96 in fraction of seconds. So this is the steepest slope. Okay, so then from maybe 96 to 97 will be little low. So 97 to 98 may be the slowest, and if you have whatever, so this part then becomes, finally maybe generally it takes 1 minute to 2 minutes to get it steady. So this would, so here maybe 60 seconds to 120 seconds. Eventually this is what is happening. So what you really see, there is a dynamics involved. So when you dip it, or when you try to measure the temperature, you would say sometimes it takes to reach the required steady state. So this is, so you would most likely see this would be your characteristics. This is fundamentally modeled as a first order system. So you have your k by tau sensor plus s plus 1, because eventually it will reach the steady state, but it takes some time. So this is a classical first order system. So Oftentimes, I'm saying this is for temperature sensor. Most of the sensors works like that because sensors would eventually give you the final measurement value as you want to measure, but it takes, so only problem is there is a dynamics. It is not that, it's just not the delay. So see, there are two things, right? One is delay and the dynamics. So if you measure your temperature like this, so this is a delay. So we call it as transport delay or whatsoever. So which essentially means after some time, it just gives accurate reading. So these kind of temperature sensors also are there. So you look at your thermal guns, which now widely used to scan the temperature. It most likely behave like this because there would be some time to scan. So that is this delay, but it would just give you one shot. So it won't take any time to bring in a dynamics, but it would be just bring in a delay. So when you, so I guess you might have used or might have seen when you were working with a thermal gun or even a or infrared thermometer. So there is some time because your device has to scan your temperature, then it would be just a one shot jump. So this is a delay and this is a dynamic. So you will have to figure out what is the real dynamics of your system. So here I am just talking about your temperature. So you may be controlling some other variable. For instance, it could be flow, it could be pressure. So you'll have to identify what is the dynamics and you have to correctly bring in that information. Okay. So give me a minute, just a second. So, sometimes it's closed down. Okay, so you could see if the process temperature, process time constant is very high compared to this, the sensor time constant, you can even neglect this. For instance, your time constant of the overall process, maybe let's say 5 minutes. And the time, so I'm saying tau, it is 5 minutes. And your tau measurement, also tau sensor or time measurement is 20 seconds. You can conveniently ignore because this is anyway taking the lead, so you can give as it is. So you have to judiciously choose whatever is the case. So now coming to the controller, so it could be P, PA or PID, whatever, you have the controller transfer function. Okay. So yes, so this is okay. So here is some catch. Okay. So look at where you are keeping your controller. So your measurement. So you look at this whole diagram. So measurement sensor is going to comparator and comparator is going to the controller. So comparator, you are comparing with the actual signal. So let's say how it works. Okay, so this is your comparator and this is controller. Okay, and you have a signal coming out from your measurement. This is your measurement sensor. So this is coming in here, okay, and do some comparison, okay, with respect to the set point. So this is like an addition term. Okay, so you might keep a plus here because you would keep a set point in the sense that this is your actual measurement. So this, you take the error and this error is going to the controller. So the controller can be anything. It could be P, PI or PID whatsoever. So let's assume you are keeping a PI controller. It could be PID also, PE also, whatever. So I'm just trying to help give a perspective here. See, this comparator is, so the thing that is going inside the comparator is the error. Okay, the error that is going to the so the thing that coming out of the comparator is the error to be given to the controller. And here the measurement error is in signals, milliamperes, or possibly in volt, who knows? Because the sensor has already converted your variable into the signal form. And comparator, you are trying to compare it with this signal. You see that this is a signal. So your physical, so let's say you wanted to so your target set point is 100 degrees C, assuming you are doing a temperature controller and the target set point is 100 degrees C. Okay, 100 degrees C, definitely this is a signal which is equivalent to some temperature. Let's say the measured temperature is 90 degree C. So it would be some, maybe let's say this is like 8 milliamps is the signal coming in, and you wanted to compare it 100 degrees C. So 108, there is a calibration mismatch. So you need to have a mechanism to convert this 100 degrees C to an equivalent signal. So you have to look at the sensor. What is the dynamics of the sensor? You apply the same thing over here. So this 100 degrees C now will be an equivalent signal. This may be, let's say, 10 milliampere. Okay, when you do this conversion, so this 10 milliampere minus 2 milliampere would be 8 milliamperes, will be 2 milliamperes. So this is the error signal that is going into the controller. So if you write it 100 here, there is no, technically it doesn't make any sense, because your overall system here is operating in the signals, which is either between 4 to 20 milliamperes or 1 to 5 volt till your actuator. So if you submit the variable physically as it is, so it would cause a huge, it would either cause an error or cause a confusion, because really you need to have a signal equivalent of this temperature to compare it with your actual measured temperature. So this is what I wanted to say here. So see, look at here. So when you look here, you would see your original variable you need to compare is the mass fraction. Okay, the mass fraction, you need to have a mechanism to convert this into what you call the mass fraction signal. You see here the mass fraction in actual variables. So after this particular blocks came, it becomes signal, because it is in a signal equivalent. So here also now signal, so you can compare and it goes to the controller. So okay, so I will just do this and we can just give me a minute. Okay, so the next one is the current to pressure transducer. So we have seen here also, because we need to have this current. Controller give you some electrical signal output. So now you need to operate a control valve, which is a mostly a pneumatically or hydraulically operated device. So you need to convert this current to pressure. So that would be another conversion. So it's a device that you buy and keep. So like control valve. So control valve have it. So it's a device that you buy, right? So and you keep. While controller is also a device. Let's assume that it's a hardware having sort of resistance, capacitance, inductance, everything. Huh? So ITP converter is also a device you can buy. It would be like a small box that you can hold in your hand. It would take something like this. Okay, so it most likely works by means of certain. So inside your ITP converter, it takes what you call the current, and it gives you, and you have it. Okay, let me just draw sometime somewhere here. It's like a box, okay. And of course, your electrical signal is going inside, which is coming from your controller, and it also has a pneumatic line coming in here, some compressor. Output is also a pneumatic line. So the way I put, so this is indication of pneumatic line, okay, while this is an indication of electrical signal. So if you put two cuts on a line, in a control sense, it indicates that it is a pneumatic line. Okay, so now what is happening? So compressor would supply ample air. So this is pressure equivalent to compressor pressure. So you might get compressor pressure, whatever its rated pressure, it would draw a line and keep in here. And electrical signal is also going inside. So there is some what you call inside this. There are some ITP converter. So it contains some resistances, okay, some bellows, some diaphragm, so that this pressure is now either this would be at a higher, because this is supplied at a rated compressor pressure, and you only need here 3 to I think 15 psig. So there would be this, so you have to decrease this pressure, so by means of some resistance, bellows, array, whatever. So and based on this electrical signal, so it get actuated, so it would gives you exact pressure equivalent. So see, it is a very interesting and complicated process. You are now converting an equivalent signal. So unless electrical signal to a pneumatic signal, so unless you calibrate your system properly, so you would prone to have an error. So you, when you buy this ITP converter, it would give you the calibration details, how to calibrate and things like that, and you have to do that before you implement it. For instance, so you take this ITP converter, okay, supply 4 milliamperes, okay, and check what is the pressure that you are getting. You should get 3 psig. Okay, 20 milliampere, you should get 15 psig. If it is not there, you have to fine tune whatsoever. So you have to test this, and once you test and you keep it inside, then the electrical signal goes inside and the corresponding pressure signal comes out. So see, so which essentially means that there is a conversions, right? So this is 4 to 20 milliampere to 3 to 15 psig. So you also need to have a conversion, and there may be a delay too, but generally it is a fast process, because pneumatic signals are very fast, unlike, so it's like a pressure signal, so most likely it may be fast. So again, it got, I don't know why this is happening. So eventually it is most likely a conversion, as you see, pressure, it takes something and takes outside. So, but it can also have a dynamics. So you, let's say if it is specified that it follows a first order process, you will have to obey it. So here we are just assume that it is a scaling, but it could be a total conversion too. So the last one is the control valve. So control valve is basically taking in your pressure signal and opens up to the valve, opens the desired valve, so that the necessary flows can be established. So control valve dynamics mostly be modeled as first order system. Why? Because so let's say this is valve. So how the valve is being opened? So you have this valve, okay, and this is the diaphragm, and based on your pressure, apply pressure, this diaphragm would push or pull the stem. So this is your stem. The stem would go up and down, and basically the stem length is what controls the flow, because if it is fully up, there is no block. Okay, if it is fully up, this line is fully open. If it is fully plugged, there is no flow. Okay, so based on the pressure, or rather, you can see how this guy opens up. So you can see the stem position. versus your airflow, you would essentially see that. So there are, so we'll again talk about that maybe separately. It would most likely open like this. So in fact there are three types of valves. One is based on the stem position opening. You would see that linear valve, quick opening valve, and something known as equal percentage valve. So linear means that this airflow stem position would be linear in nature. Quick opening means that for a smaller flow, you would see a larger opening, something like this. Okay, and the third is the opposite of that, which is called equal percentage. So it would be smaller for a smaller airflow, the valve opening is less, and if you put higher airflow, you would see. And again, you will have to buy this. So when you need to buy a valve from the market, you have to specify what sort of valve do you need. So how do you decide? It is a properly industrial oriented decision in the sense that if you don't have any bias, so if your airflow and stem position has to be linearly operated, you have to buy a linear valve. Okay, but if you need to have very fast response, let's say if you are working with a safety critical application where your response has to be very fast, okay, then you will have to possibly go and buy a quick opening valve, and the other way around if you want a slower response. So because if for instance you're adding a chemical or a chemical line, okay, excess of that makes your overall process overall product quality deteriorated, then you will have to operate in a very careful fashion. Every opening it would only open up little bit, so you have more control. So here you see this is unbiased, which is like a linear, while this is uh, very sensitive because it opens up quite fast, while this is more controlled. And there are many others. So these are three basic categories of valve, and you have to buy. So see, when you design it, which essentially means that you are buying this from a vendor. So you have to specify based on your application, your experience. You have to say, I need a linear valve. I need a quick opening valve. I need an equal percentage valve. And once you buy this, you will get so it's instruction sheet. You will have to read their instruction sheet very carefully for any sensor that you buy or any actuator that you buy. It would give you its calibration detail. For instance, if you are assuming it as a first order dynamic, it will say the valve dynamics is first order having a gain and a time constant this. You would say that the valve dynamics is having a gain this and what they call time constant this. Otherwise, what you, let's say if there are no information, it's likely. So let's say if you buy from some vendor, but most of the standard vendor will be asked to provide this information. If you don't provide this, and if you don't get it, so what you would do, okay, so you would supply air line and keep your control valve in line, okay, and this you most likely will do in your process control lab next time, okay. So you would take a scale, okay, so then you go back and see. So you would supply 3 psi pressure, and so in fact and check what is the stem length. So let's say it is 4 centimeter, and you start supplying 4 psi and say whether, assuming that it is air to open valve, your stem would keep on moving up, okay. So you would say that it is 5 centimeter, then you apply this till 15 psig, and you got, it would be possibly some 10 centimeters or so, who knows. So so now what you got your pressure and your stem length, and you would try to fit it. So then you try to plot, okay. So here your stem position, and this is your pressure. So 3, 4, 5, 6 up to here. So when you see that it follows like this, it is linear. Okay, if it follows like this, it is stock opening, and if it follows like this, it is equal percentage. So this would also might happen because when you buy it and you don't have any information, and once you have this sort of a dynamics and you fit it, you can know what is 63.2 percentage and what is your final opening. You would get your K by towers plus 1. So your overall control system, you will have to add up everything. Okay, so so let's start with the process. Okay, so this is your process, and this is the disturbance term that is adding to the process, so it would get summed up. Okay, so you would measure that by means of a measurement element, assuming that. So here what they have done is Km by tau ms plus 1. Okay, so assuming tau, or rather if you know that tau is much greater than tau m, so you can neglect this. So that is what they have done over here. Okay, so it is going to the comparator. So comparator, you have your original mass fraction. So you are measuring the mass fraction. So see, you need to control your mass fraction for this particular problem. You need to control x. So your x should be, or rather xm should be equal to your x set point. So this is the control problem here. Measured concentration should be equivalent to the set point concentration. Okay, so now you use the same conversion. So you used your physical variable is converted into the electrical signal. So your physical variable should also be converted into the electrical signal. Go to the comparator, controller, I to P, control bar, and finally that is going to the process. So this overall assembly of all the transfer function is known as the closed loop system. So because it is loop is closed, you are taking a feedback line and you have closed the loop. So this has to be continuously operated if you need to measure, have your xm, which in this case your x measured, if you want to make it to x set point. So at this point, I will ask if you have any clarification on this.
Hello, sir.
Yeah.
I just wanted to confirm it once that wherever any conversion of the feed into an electrical signal takes place, then the transfer function is associated with that of a transducer only.
So could you tell me that again? I think it is Shruti, right?
Yes, sir.
So you
Sir,
tell me exactly. Yeah.
sir,
So
I'm
let me
asking that
understand your problem.
wherever there is any conversion is happening, for example, sir, here in this figure, YSP is getting converted into an electrical signal. Sir, in
Say
the
here,
previous,
right? No,
yes,
here,
sir.
here. This one. Correct,
Hmm.
correct.
Hmm. So,
So
sir,
okay. So if I understand your question correctly, this conversion factor has to be exactly same as this conversion factor. Is that the question?
sir, please repeat it once again.
So this conversion, so for instance, your set point is converted into electrical signal. Here your physical variable is converted to electrical signal. So your question is the transfer function of this conversion. So here it is Km, that is exactly same as this Km. Is that your question?
Yes, sir. And also, sir, how that KIP is different with that KM? Is it
Where is
because the
KIP here? Okay, here
sir,
this guy.
sir.
Okay. So there is a big. Okay, so it's a good question. So let me explain that. Okay, so there are two things. Okay, one is physical variable to electrical signal. Huh? So let's try to understand the level of changes that is happening inside your system. Physical variable to. So this is one standard. So this is done by sensor. So there is also one more level of change is happening. It is electrical to pneumatic. So this is happening at I to P. Okay, and this pneumatic valve is opened so that it gives you the desired flow rate so that it can affect. So now coming to the sensor. So sensor will have its own dynamics. For instance, tau m by k, km by tau s plus 1 whatsoever, or it can be just km for simplicity. So this happens in the transducer or sensor. And when you also supply, so let's look at that block again. So there is this comparator and this is sensor output coming in. This is your sensor. And now you have an intermediate conversion for your physical variable, and this is your original physical variable. So here is your original physical variable. I will say ym, correct? And here this is ysp. And this is plus, this is minus, and this is going to this is the error as signal going to the controller. So whatever. So so let's say your transducer doing a conversion ym2. I will say if you wanted to really make it as a different thing, I'll say ym signal. So I don't know, from the figure it is written like that. It is okay, mildly, I think, yeah. So it has a very different notation, but that's okay. So this is ym signal. This is the electrical equivalent, and this is your physical variable. You have to do the same thing over here. So let's say your transfer function here is just a scaling factor km, or whatever km by tau s plus 1. So you would do the same scaling to your set point. So this may be a 90 degrees C, and you are getting 8 milliamps here, and your set point is 100 degrees C. Okay, you are getting, let's say, 10 milliamps here. So this sensor, what is the conversion thing? The same thing applies here unless otherwise specified, because you are converting the same sensor equivalent thing over here. No? So this transformation and this transformation generally are one-to-one unless otherwise specified due to some specific reasons. So this is, I think this probably answers your first part of the question, isn't it? Isn't that, Shruti?
Yes, sir.
Okay, so now coming back to your second question. So your second question, why this guy is different. So this is it should also be, so this is error is going, so this is your controller output, which I'll call it as P. Okay, and this is going to the pneumatic control valve and later to the controller. So your question is this, why can't this also be K? If I understand your questions correctly.
Yes.
Is that right? Okay, so this can't be Km. Why? Because we are not doing electrical to physical transformation. In fact, it should have, even if you do electrical to physical transformation, this should have been 1 by Km. Is that agreed?
Sir. Yes, sir.
But we are not doing electrical to physical. We are doing electrical to pneumatic. Okay, so this is, in fact, this is another space, right? So pneumatic will go to, so pneumatic valve would actuate your stem levels, and that would affect some other variable, then it become a physical system. So this is not electrical to physical variable directly. If it was the case, this should have been 1 by km, not km, 1 by km, because whatever forward transformation that you have done, you have to take an inverse. But this is not what we are doing, but you are doing a third transformation, electrical to pneumatic. So this tend to be very different transfer function. This could be some KIP or something. Is that clear?
Yes, sir. Earlier I missed that pneumatic thing, electrical.
Yeah, no, I think this has to be very clear. So I think this may be even for others. I think I hope this would be useful. And let's say, okay, so even if, let's say you are doing this inverse transformation, this will not be Km. You have to mind that this will be 1 by Km. Good, got it? Inverse of that, no, whatever you have done, you're doing
Yes.
it back.
Yes.
So any other confusion on this? So this is like the real system that you are going to deal in any industry. So now we have to learn how to tackle this big guy, because earlier we are not looked into this. We are looking process as an isolated variable, controller as an isolated variable. We did not even talk about control valve. We did not even talk about measurement device. And now we added up everything, and this is, of course, it's a very cluttered figure though. So this is the overall structure that you wanted to learn or you wanted to play. And what is the problem here? Let me tell you, the problem comes when, so this GP, so now let me go to some notations. Okay, GP is process, GV is control valve, V stands for valve, GC is controller, okay, GM is your measurement, which is the sensor. This is the transformation from physical variable to the electrical variable of the set point, and GD is the transfer function corresponding to the uncertainty. And both of them has to be added. Now what is the problem? So now your aim is to make Y, which is the output, which is YSP, which is the set point. So you want this guy, sorry, oh my goodness, just give me a minute, I think my pencil charges. Okay, so just to continue, you want your Y is YSP and Y to be same. So you want this to be same. To achieve that, okay, you have now added up n components inside. If it would have been one controller, it is okay, because controller cannot work alone. It would bring in a big handicap to him. To aid in controller, you put a sensor. To operate the controller signal, you put a valve. Okay, and to feed in the controller, you put a comparator where you do another transformation. So what is the problem now? So this guy is also called as, so original Y, so okay, just for the notational safe. So if YSP is the original set point, so Y tilde SP is also known as internal set point, which is signal, electrical signal equivalent of the original set point. Okay, so what have we done? To have a, to do a simple job, we put in lot of things, because all of them cannot work alone, right? So you have to have, you put what to aid the controller, you put the measurement device. To operate the controller, you put the valve, and between that, so I2P is virtually missing in this. So I2P could also be added between controller and the controller, if that is the case. If otherwise you do that, this I2P conversion is 1. Okay, so so now your overall dynamics is controlled by all of these independent elements, and let's say one fails to perform suitably, your entire control system is affected. So what you have to do is, so you need to develop a transfer function between everything between Y to YSP, so that Y, you need to make Y by YSP equal to desired value. So you need to build a transfer function that containing everything inside, you see. So YSP is outside, so you have to look at the way it is. So again, cluttered. Okay, so Y is outside and YSP is outside. Rest all is inside. So you have to make a transfer function that kind of capture the dynamics between this end to left end to the right end. Such transfer functions are called closed loop transfer functions. Why? Because you are now modeling the entire closed loop. So closed loop has, it is not an open loop. So there is a difference between open loop and closed loop. Open loop, which means that you have only forward dynamics. So you have a controller, you have a something, your process output, Y, controller, process output. So this is closed. You have taken something, fed back, and made some controller arrangement, everything. So this is much more difficult thing to do a control. Okay, so another question that I wanted to make. So generally YGD. So again related to notation or representation, don't get carried away. So GD, sometimes you would see GD sometimes also be added over here. So in that case, your original GD again would be so you see your GD is, so then you have to, instead of this new GD, you'll have to write a GD star here, such that your GD star is GD by GP, because it's product transfer. So it's more of a notation. So this may be useful and this may be also used conventionally. If you are writing in this fashion, you will have to adjust the transfer function, because by obeying the multiplicative rule of the transfer function. Okay, so now coming to what? So can we do this reduction? So from n to n, can we reduce it as a simple transfer function? Because there are many things. And it should have been easier if it was just a forward thing. So then why? Because we have learned this particular rule, right? If there are blocks in series, the y2 x3 become, so here see u is equal to g1 g2. So your input u has been transformed into 3 different transfer functions to get x3, and by multiplicative rule, it is u is equal to, rather x3 is equal to g1 g2 g3 times u. And again g1 g2 g3 can also be written as a, replaced as a new g, because eventually when you multiply it will boil down as a single transfer function. So it would have been easier if you don't have this feedback loop. Then it's just a forward multiplication. Now there is a loop that is coming in, there is a negative sign that is coming inside. So this has to be handled little bit carefully. Okay, so such thing is called block diagram reduction. Because there is a so there is something, there is a feedback loop which was not there in the original. So now we learn how to deal with this feedback loop. Okay, so before we learn how to do it, so we will have to develop transfer functions for two different cases. One is technically called as servo problem. It is also called tracking problem. Other one is called regulatory problem. It is also called as disturbance rejection problem. These are the two fundamental problems. We'll see what is this disturbance rejection. So these are the two different categories of control problems that you would deal with. So what is servo problem or tracking problem means that, okay, so this was the set point, so XSP, or rather YSP, it was like this, then you change the set point. And servo problem essentially means that you have to track it. It was like this, so it changed, so you will have to do a tracking. So this is your YM, this is your YSP. And the second is disturbance rejection problem. For instance, your process was operating like this, and a lot of disturbance came in. So from here to here, because of YD, lot of disturbance, the process started oscillating. Okay, now you have to reject that disturbance. Controller should reject the disturbance and come back to here. So here is the disturbance rejection. So for again simplicity, we will learn this step by step. We will first talk about servo problem and regulatory problem. Later, if you need to combine both, you can do that. Okay, so it's like A plus B. So let's try to look, because just to avoid complexity, so just we'll first look at how a servo problem works, how a disturbance rejection problem works. So the main difference comes in your transfer function. So see, when you model your transfer function, it's always going from front to back. So your y, we are now looking servo. First of all, let's look at y. Y is a summation of yd and yu, yu plus yd. Huh? Okay, so now I can do one more step back. It's always going from, so it is like walking backwards. Huh? Always working backwards or solving backwards. Okay, so yu is u times gp. So yu is u times gp, and yd is d times gd. So when you look at servo problem, you generally assume, so as we seen here, so it is, you are mostly focused in tracking performance. So there is, we are not worried about the disturbance at that time. You need to track when you do a set point change. So okay, so we can conveniently put this yd is to be 0 because there is no disturbance at the moment. Okay, so because we are only looking at set point changes. In the other case, we will only look at disturbance changes, and if you need, as I told, you can combine a plus b also. So how to write this now? Okay, gp. So what is gp? gp would be, okay, e times, again working backwards, okay, e times gc times gv times ep. So that is your, so look at this, okay. So gp times e, huh? So just give me a minute. So what you really need is u, right? So u times gp. So u times gp. So now how do you get u? So u would be e times gc, okay, times gv. So e times gc, gv, gp is the whole thing. Okay, so I will stop in quickly. So, and what is E? V is happily y set point minus phi m. Y set point minus phi m. And what is, so it is, in fact, this is y set point tilde, which is called the internal set point. And what is ysp? It is km times ysp. And what is ym? It is y times gm. Okay, so now what you only have to do is rearrange, okay, such a way that y and ysp in one side and rest everything in the other side. You can do this algebraic manipulation. Okay, so that, so you would get something. So that is known as the closed loop transfer function for servo, and you would have to notice two important things when you get it. So it would, so the structure would be something by 1 plus something. You see this, okay, so I will have to write it like k1 by k2. So something by 1 plus something. So what is this on the numerator? Numerator would be your, if you look at the product of the transfer function, it would be just from here to here. You can do it yourself and figure out km gc gv gp, km gc gv gp. So it is the product of all the forward transfer function, and in the denominator you have this 1 plus term that would contain, okay, except things which are out of the loop. So you cut here. So gc gv gp and gm, gc gv gp and gm. So, and this particular 1 plus term is called, we'll talk about that open loop transfer function. So I'll stop it here because it's already 11 o'clock. So this is what, how do you reduce your complex transfer function into simple transfer function having a numerator and a denominator. Okay, and sorry for exceeding the time, and I'll see you tomorrow, I think Friday. Okay, bye bye.
Thank you, sir. So please stop the recording as well.
Yeah, please. Thank you.